Okay, so hi, my name's Noel Gorlick. I'm one of the co-founders of Google Earth Engine. And today we're going to do a Earth Engine hands-on training workshop. The agenda for the day is I'm going to talk up here for about an hour telling you what we do, how it works, that sort of stuff. And then we're going to do 3 hours of hands-on typing. You're going to make a lot of mistakes. That's on purpose so that you learn how to deal with those mistakes here. And then when you go home, you'll actually be able to conquer them rather than going, I don't know what this means, and quitting. Hopefully by the time you leave, you'll have all the tools you need to go do your research on Earth Engine, and we're happy to support you, okay? So I used to send spacecraft to Mars. I got to work on every American Mars mission after Pathfinder that didn't crash. So that was 5 Mars missions. I was the data guy for a lab. We had a small lab. If you have a successful lab that processes lots of remote sensing data, you have a data guy. It's just kind of a requirement to have a successful lab. And that was me. Ended up building up some pretty big teams because we worked on a lot of missions at the same time. But ultimately, I was new at the job when I started 30 years ago, and I made a ton of mistakes. I made 20 years worth of mistakes and fixed them and learned how to fix them over time. And then I got to go to Google, and they said, what do you want to do? And I said, I want to make sure no one ever has to make those mistakes that I made. They can make all new mistakes, but all the things I learned about data processing and data handling and downloads and file formats and projections and resolutions and storage and network and routers, you shouldn't have to know that stuff. You should be able, as Earth observation scientists, to just do the Earth observation science and not have to do downloads and file formats and storage and network and bandwidth and clusters and all that other stuff that I went to college for 8 years to learn how to do so that you don't have to do it. So that was sort of the impetus for how Earth Engine came out to be. I like to call myself a software engineer. I like to think that I'm a highly educated, sophisticated guy, but at the end of the day, I'm basically an IT guy. My job is to build a bunch of IT infrastructure so that you don't have to fiddle with a bunch of IT infrastructure. When you get hired at Google, you get put on a team, and they expect you to be useless for about 6 months because the massive machinery inside of Google is really complex. And we hire PhD-level software engineers to drive it and build it, and it requires a computer science degree to make work. I don't think you should have to have a computer science degree to be able to process a lot of remote sensing imagery. And so Earth Engine is the piece of software that sits between Google's massive parallel infrastructure and you. And when we built it, we were thinking about you very specifically. It's designed for scientists. It's not designed for software engineers. And in fact, my computer science buddies, when they look at it, they go, wow, this is really weird. What did you do? But if you do lots of remote sensing analysis, we think it's kind of exactly the right shape for a lot of the things you do. And everywhere that we've got to make a decision between computer science or Earth observation science, we always made the choice to favor the Earth observation scientist. But because it's built on this giant parallel processing system that Google uses to harvest the internet every day and do all those other things that Google does, we've got zillions of machines that you get to use, and you don't have to worry about how many machines you're using. You just use them, and stuff happens, and you get to move on and do your science. When we were making it, anytime you build a project at Google, you sort of set your goals and your non-goals. Our #1 goal was to make it easy to do this very large-scale analysis. And what we wanted to specifically promote was scalable and shareable workflows. So I want you to be able to do your science and do it fast and do it well. And I want you to be able to not be limited by scale. If you want to process 1 Landsat scene, that's fine. We're maybe a little overkill for that. If you want to process 1,000 Landsat scenes, that's great. We're probably right in the sweet spot. If you want to process every Landsat scene ever taken, we're kind of your only option. There's really not a lot of places on the planet you can do that. And that's what we're looking for, scale. We want to make it easy to do, build your algorithm and then scale it up as far as you want. And then once you can do that, so let's say you're building a drought detector or a deforestation monitor. What I really want you to be able to do after you get your science out of that is hand that to the people that actually are dealing with drought and deforestation. I want you to put your science in their hands so that they can actually do the good work of making sure people don't die from drought and making sure we still have forests in 10 years. So scalable, shareable workflows. That's what we're all about. And then finally, I want you to hand those algorithms off to people that probably would never be able to use them otherwise. So if you're the guy working on in the Ministry of Forestry and Beekeeping in Peru, and your job is to stop the illegal logging, you probably have one 12-year-old computer, you probably have a cell phone's worth of bandwidth, you probably have a high school education if we're really lucky, but you know your ground data really, really well. So that guy's not a remote sensing expert, but he really needs the tools to be able to do the remote sensing to manage his forest. So I'm trying to enable you, traditional remote sensing users, to enable other non-traditional people to use your stuff. So I want to help 50,000 scientists. I want my 50,000 scientists to help 50 million people. That's what we're trying to do. In addition to building a tool and software engineering and all the things that you think of when you think of Google engineers, part of my team, 1/4 of my team, is specifically focused on trying to take our tool and apply it to society's biggest challenges. So I really don't know much about deforestation or drought or disaster or disease, but I know people working on those things. And my job is to travel around and find people like you, but then amongst you, there's a few of you that have this crazy idea about, well, if I just had this algorithm and that data set, I could do this crazy thing over here, like map every tree on the planet, or map all the water for the past 40 years, or something like that. And so we find scientists with these large, ambitious projects that are clearly in the public good, and then we focus energy and effort on trying to make those projects successful. So I want all of you to be successful, but sometimes we find that person who's like, wow, if I could franchise this project across every UN country, then awesome stuff would happen. So we often look for and try to support those projects. One of the things that makes us super popular is that we have a very large data catalog of processed, ready-to-use data. My data guy caught me yesterday and he says that number is actually 20 petabytes, not 10 petabytes. He takes that very seriously. But in our data catalog, we've got every Landsat scene ever released by the USGS. We've got all of MODIS, all of Sentinel-1, all of Sentinel-2, 3, 5P, VIIRS, 17 other satellites, and in total, about 500 other data sets. I need to update my slides. And all those data sets we have because a scientist asked for them. So we preemptively loaded all the Landsat data because we knew a lot of people wanted Landsat data. But everything else we've got because a scientist said, hey, I use this data set here and I'd like to use an Earth Engine. Can you go get it for me? And so we have a data set request form. You type in where we get the data set from, what it's useful for. People vote on it. And then every Monday morning, my data team takes the top 5 of those entries and goes and tries to bring them in. And sometimes it works and sometimes it doesn't, but that's their job. They want to go deal with file formats and downloads and resolution for you so you don't have to do it. We want to do it once, so it never has to be done again, basically. When you're working with things like Landsat data, you often want other data sets like aerosol opacity or land cover or something to go with it to do your analysis. So we've got lots of other data sets besides just the satellite imagery. And then lots of stuff that's not actually remote sensing data at all. You've got climate forecasts, climate models, a whole bunch of stuff. But the important point is it's there because someone asked for it. So if you're an oceanographer and you look at Earth Engine and you say, you know what, you don't really have a lot of ocean data sets, that's because you haven't asked for them yet. So let us know what you want. This is sort of a peer-reviewed, or what's it called? There's a term in social networking here. It's a peer network, right? So you're telling us what data sets you value, and then other people say, yeah, I value that data set, and we go and get the most important ones first so that they're there ready for you to use. And finally, you can always upload your own data into Earth Engine if we can't get the data or we didn't go get it for you in time or something like that. You might have bought a bunch of planet images or digital globe images, some Pleiades images, something like that. I can't go buy those for you. I can't download them for you. But if you've got them, you can upload them into Earth Engine. We give you a pretty generous bucket in which to put your data, tables and images. And then you can use those exactly the same way you use our data. You can mix and match. The system can't tell the difference, except all the stuff you upload is private to you until you want to share it with someone else. So you won't violate any commercial licensing terms if you put your commercial imagery into Earth Engine, because no one can see it but you. But if you want to share it, if you've got data you can share and want to share, we try to make it really easy to do that. Okay, so some pretty pictures. We'll call this the motivation section. When you've got all that data, you can do some cool stuff. This is a scene from southeast coast of Borneo from Google Earth in 2012. When we made Google Earth the first couple times, the way we made it is we found the best image we could, and we cut out good big pieces of it, and we stuck them together into a big giant mosaic of images. And this was the best image we could find for the southeast corner of Borneo. It's pretty cloudy down there. This scene is full of clouds, but there's actually about 25% of these pixels that are still good. So if you take these 25% of the pixels, the 25% of the pixels from the next image, the 25% of the pixels from the previous image, and you put them all together, you can make a cloud-free image. This image has issues. It's not perfect. You can still see some Landsat scan line problems. Any 2 pixels in this image might come from different times. So Borneo is cloudy, but not that cloudy. So this might only be a month or 2 months worth of images. But this pixel might be from June, and that pixel might be from August. And that's just something you have to account for when you're doing your science. But you have to admit, this is a way better image to try to work with than this one. Yeah? So at least you can get somewhere. Another example, this is the Isle of Mull up in the UK. It is apparently this cloudy all the time. Although I said that when I was in Dublin, and someone said, I was there yesterday and it was beautiful. But generally, it's a really cloudy place. And in fact, it took us 5 years to get enough pixels to be able to make this cloud-free mosaic. And in places in northern Canada, the same thing happens. You might need 5 years worth of imagery to get enough pixels to make a complete cloud-free composite. Now, obviously, if this is 5 years worth of pixels, you're not going to do any type of crop analysis or phonology computations. But if you happen to be coastal morphology or some other slow process, at least there's things you can do with this image that you otherwise couldn't do at all because of the clouds. So you can do this at bigger and bigger scales. This is, again, a screenshot from Google Earth in 2012 for all of South America, and this is what it looks like today. And those base maps in Maps and Earth were made using Earth Engine, hence the name. We make Earths, give or take. And so you've probably seen the global map in Google Maps or Google Earth. It's this nice, pretty image. And so clearly we can do it for an entire year. But actually, the Landsat data goes back 32 years. So we were actually able to take all the images from every year and put them together into a composite and then make 32 composites, 32 images. And if you give any engineer at Google 32 images that look even remotely similar, the very first thing they're going to do with it is make a video. So that video looks a bit like this. No cats, but it is at least moving around. You can see it's a video. And that's not particularly impressive until I point out that this is a 27 terapixel video. Oh, excuse me, 24 terapixel video. It is full resolution Landsat for 32 years, and you can zoom in anywhere in this video and see the full resolution pixels animated for 32 years. And that looks a bit like this. So this is Las Vegas, Nevada on the left, and Lake Mead on the right. And over those 32 years, Las Vegas basically doubles in size, and somewhat coincidentally, Lake Mead halves in size. So without doing any image processing, without knowing anything about remote sensing, you can actually look at this image and try to use it for planning purposes, right? Like you can plan, should you live in Las Vegas or not? Another example, this is the Arabian Desert. In the mid-90s, the Saudis decided that they were importing all their food, and maybe that wasn't the best choice. So they put 2,000 farms in the middle of the desert fed by aquifers, and you can see them just come into existence. They are center pivot irrigation farms, and so they're little circles. And you can, in the past few years, they decided that they're depleting their aquifer, and maybe that wasn't the best choice either. And so you can see almost the entire lifetime of this experiment from bare desert up to farm and sort of back down, all in this data. As a guy that used to send spacecraft to Mars, I really like this image because we have a word for what's going on here. This is terraforming. This is what we're going to do to other planets when we get to them, for better or for worse. It's going to look just like this. So human scale activities, we knew what that would look like. It's obvious that Las Vegas has grown a lot in 30 years. There's a lot of stuff in this data that we never thought we would see. This little town here is Pucallpa, Peru, down in sort of the middle of Pucallpa, middle of Peru. And that's a river meandering by Pucallpa. And over the course of 32 years, that river moves as much as a kilometer a year. And everybody knows that rivers move around. We have a whole term for it. It's river meanders. That entire area out there is full of oxbow lakes and things called river meanders. We academically know rivers move around, but no one ever expected to be able to see it at this kind of scale. And my video is a little, it looks way better on my screen, but you get the idea. One more example. This is Cape Cod, Massachusetts. That is sand migrating down the coast of Cape Cod. And then somewhere around 2012, this happens. Anybody know what that is? Hurricane Sandy, just wiping out the beach. Any coastal processes people? Not one. I don't get a lot of, oh, one in the back, woohoo! So I claim without proof that this is just pure gold for coastal processes people. This is exactly the kind of data that you want to work on. Am I right? Yeah, okay, more or less. All right, so anyway, the data's there. You can just show up and use it. You don't even have to log in. Anybody can access this data. And in fact, we released all these videos as a feature with Time Magazine called Time Lapse, just because the pun was too good to pass up. So they did a whole bunch of stories, just like I told you, but with a bit more science. And anybody can go to the Time website and see this, or the Google website and see this. And people do. So you can actually even embed this on your own website, and people do that. And we will see when people come from your website, like it's web refer, everything happens on the web that way. And so we'll come in some random Monday morning and see 30,000 hits from a little town in the Ukraine. And we're like, what the heck's going on? And one of my Russian-speaking engineers will go hunt down the newspaper article that says, in 1987, when the dam went in, this happened to our town, and we shouldn't let it happen again. And they post a link to time-lapse. And every single person in that town clicks on the link and goes and looks. And so 30,000 people that have no idea what remote sensing is, no idea what Landsat is, no possible way of ever processing this data to do anything with it, now have at their fingertips the ability to access and use this data. Total democratization of this data. And that's what we're looking for. If you remember, I was trying to enable non-traditional users. That's pretty much the summit of non-traditional users right there. So it worked out like we were hoping. Personally, in my career, this was a watershed moment, because this is the first time in 30 years my mom had any idea what I do. And she's like, oh, I get it. OK, cool. So I always have to call out mom here. All right, so what? So you made a video, big deal. Story number 2. These guys are the Surowi Indians. They live in that patch of the Brazilian rainforest down in Rondônia. And the Brazilian government said, this is your land, here's your border, do with it whatever you want. If you don't want people to log it, keep them out. And so they do. They walk around every morning with bows and arrows, keeping loggers off their land. And sometimes it doesn't work. You can see a few spots down there at the bottom where they've had deforestation. And so they came to us. Their chief went to college. He was the first member of their tribe to go to college. He's a pretty smart guy. He's a good politician. And he came to us and said, hey, look, you can see this deforestation happening from space. We can see it in Google Earth. But by the time it gets into Google Earth, it's too late. That's a year or 2 years after it's happened. Can you help us figure out when it's happening right now? So that was sort of the societal good impetus for Earth Engine. The very first incarnation of the idea for Earth Engine was actually called Google Trees. That lasted for about a day, and then we went on to something else. But that was the idea. Count trees, be able to do rapid deforestation monitoring for people like this. So we built them a tool. This is not it. This is version 3 of that tool. This is what's on the web right now. But it gives you an idea for the power and speed and simplicity of Earth Engine. This is just one web interface that we put on top of the underlying infrastructure. And the way it works is you pick some data. So this is a Landsat composite that's already built. You draw a couple boxes saying this is forest, this is non-forest. And in about that much time, we're able to make a binary map that says, OK, the machine learning says this is forest and this is non-forest. And now you can count pixels, you can count area, you can do change detection. And you can see that somewhere in this image, there were trees there last week and there aren't trees there this week. Maybe that's where you should be focusing your mitigation efforts. And you can narrow down where you need to look or where they need to look. The whole thing takes about 5 minutes to train even non-English speakers on. We haven't even translated it to other languages, but we did this with the Peruvian Minister of Forests, and he's like, that was very cool, that's nice, but what I really care about is illegal gold mines. Can you tell me where those are? And we said, no, but you can tell us where they are, mark the ones you know about, and then run the machine learning. And he's like, oh yeah, I'm going here when I get home. So he was all through a translator. Like, he doesn't speak English and we don't speak Peruvian? Spanish? But it worked really well. Lots of people use this tool. We call it the good enough tool. You should not be publishing a scientific paper based on the 45-second classification that I just showed you. But if in the morning your job is to go patrol the border, this is exactly what you want. A really quick reconnaissance tool to be able to use the latest data and see where you might need to go to look at stuff. You don't want a lot of false alerts, but you can go check out 4 or 5 in a day, and so you get the 4 or 5 that this tells you about, and you go work with them. So this is the chief of the tribe. His name's Chief Amir. Like I said, he's a politician now, and he travels around the world to UN events advocating for indigenous people's rights, wearing that hat, which is pretty hilarious. But even though he went off to college, he came back. He wants to live in the forest. He wants to live with his hunter-gatherer family, his tribe, and he should be able to do that. This is the way he wants to live. But it turns out his forest has pretty good Wi-Fi, and so he's actually able to use this right there in the forest. Thank you for laughing. Okay, so those are some interest stories. People do science with Earth Engine too. So I'm going to show you a couple of prime examples that have gotten published that we're really excited about to give you a flavor for the kind of stuff we can do. I'm going to show you 6 examples. We have 100,000 users. So clearly there are a lot more projects going on than these 6, but these are sort of some lighthouse projects that I want to tell you about. In 2012, published in 2013, Professor Matt Hansen, now at University of Maryland, made a global forest, global tree cover and loss. He hates to call it forest because that's a really loaded term. This is that map. The green areas are where there are trees, and the colored areas are where there aren't trees anymore, and the color is the year that the trees were removed, so year of loss. Just like the time-lapse data, you can zoom into very full resolution data on this and see individual plots, individual fields, and when they got harvested. This is Indonesia. When this data was published, it had a really cool effect, kind of exactly what we were hoping for. People used it to prove that Indonesia was triple logging their concessions. They were claiming that concessions were logged once every 3 years, which was totally true, but they sold that concession 3 times. And so in the intervening years, other people came in and logged it as well. They basically didn't know this. They didn't really have ways to tell it. But when this data came out, it was pretty easy to show that it was happening, and it actually affected their logging concession policy. Again, exactly what we were hoping for, or the kind of thing that we were hoping for. When we did this, this was a massive amount of computation for us. But this was back in 2012, which in internet time is forever. Right? That was a very, very long time ago for us. But it was about 700,000 scenes, close to 700 terabytes of data. Running this process took about 1 million CPU hours. And the really cool thing about working at Google is when you want 1 million CPU hours, you just sort of set the dial and say, OK, I'd like 10,000 machines, please. And that all finishes in about 4 days, which means we were able to round trip with the scientist about once a week and run many, many, many versions of this till he got what he was hoping for. It ended up as a publication in Science. I am not saying that if you use Earth Engine, you will end up with a publication in Science. That is not what I am saying, just to be clear. But it does happen. And that data is now in Earth Engine, right? It was produced in there. We rendered out the pixels, and you can use it and just pick it up and start using it, and people do. This is a website called Global Forest Watch. It is produced by the World Resources Institute, and it's their website. We have very little to do with this website, except they gave us a logo because they use us. And the way that they use us is you go and use their interactive tools, you draw a box, you pick a data set, and you say, how much deforestation happened here? And they package up a query, they ship it off to Earth Engine, we do the quantitative analysis, and in a few seconds return a number. And so here I've drawn a box, I've sent off the query, and it says 3.7 million hectares of loss between 2000 and 2013. Totally under their control, they get to decide who uses it, how it works. We're just the back-end engine that is able to do the fast computation for them. Another example, this is a project by the Joint Research Center published in 2016. It's a map of global surface water and surface water change, and I really like this project for two reasons. One is it makes really cool, pretty images, and the other is I'm on the paper. But just up front to make that clear. The way this worked is we made mosaics for every month that Landsat has been flying. So I think that was 396 months. And then for every month, we detect water and no water. And what you're seeing here is a visualization through the stack of all those images of occurrence. So a percentage of how often a pixel was water or it wasn't. And so the dark blue is places where it was water 100% of the time. The gray are places where it was water 0% of the time. And the reds are shades between 0 and 100%. And so in this completely static image that doesn't move or anything, you can actually see that this river in China occasionally floods. The water sits there for a little while, sometimes almost permanently, and then evaporates away. And so being a visualization guy, I really like images where you can see temporal dynamics in a static image. This was 4 years later than the Hansen work and 2 years ago, which is still a really long time in internet time. But when we did this, this was 3 million Landsat scenes, almost 2 petabytes of data, and 1,200 CPU years of computation. That's about 10 million CPU hours. But the output this time was not one image. It was one image for every month. And that entire stack of images is sitting in there. So there's 394, if I do that math right, 394 images in there that you can just go use for whatever purposes you want to use them for. And there's other images like transitions and seasonality and that sort of stuff. But again, and it ended up in Nature. Again, that data is just there and you can use it. So here's some quick examples of using that data. This is just pulling out some time slices, colorizing them, and animating it. And you can see the Louisiana Delta growing by almost 2 kilometers over that time period. And the amount of, there was no work in doing that. It was just picking some frames and making a video out of them. On the right-hand side, this is research by a researcher at UC Berkeley named Alex Brick, and he's a river morphologist. And he really likes this data because with it, he's disproving almost everything we think we know about river morphology. Every time I see him, I make him retell me what he sees in this slide, and I get it wrong every time. But essentially, this bit here is a type of erosion and deposition that is not supposed to happen. There are laws in river morphology that say that can't happen. And yet, here it is happening. And so for his science, for his research, what he's doing is he's getting statistics not from one river or 10 rivers or a continent's worth of rivers, but every river on the planet. So he has hard quantitative facts about what can and can't happen in rivers that move right now, because they don't all move. There's some rivers in Papua New Guinea that haven't moved in 30,000 years. But for the rivers that do move, he has all the statistics. And so he's off busy writing a textbook about river morphology instead of finishing his PhD. But maybe they go together and he gets done. 2 more examples. On the left, this is a map of malaria risk made by a group at UC San Francisco led by Hugh Sturrock, the Wellcome Trust, the Gates Foundation, and Oxford. And what they've done is they've made an alerting system that tells you when you're likely to get malaria. And the way they do that is they don't map mosquitoes from space, because you can't do that just yet. But you can map the environment in which mosquitoes can breed pretty well. So you can predict based on temperature, elevation, wind, precipitation, distance to humans, some other covariates, and actual malaria occurrence data. You can build a classifier and say, okay, you are most likely to get mosquitoes here in 6 weeks. And the people on the ground actually trying to do malaria eradication actually go out and distribute the limited resources they have of pesticides and mosquito nets in those targeted areas to do the most good with the little resources that they have. So we've been super excited about this project. It's an alerting system called Disarm. and we were very happy to be a part of it. Okay, on the right-hand side, this is actually a pretty simple example, but it leads into a bit more discussion here. So the way this worked is you're mapping urban extent over there is what's going on, and that happens to be Dallas-Fort Worth. But the way this worked is that a researcher named Paulo Gamba published a paper in JSTARS in 2015 saying, I've done urban mapping, I've done some urban mapping, and I've made some conclusions from it. But he published his code. And I said, hey, Paulo, can I use your code? He's like, I published it, do what you want. So I took his code, just Earth Engine code, I ripped out all the good science he did, and I boiled it down to the barest minimum of what was necessary to replicate his results. And then I just stuck a little loop around it and ran it every 3 years for a couple of years. In presentations like this, or especially when I'm giving presentations like this to like congressmen and people like that, I'm told never show code. But I really want to show code because this is all the code necessary to make a global Landsat composite for 1 year, and this is all the code necessary to replicate Paulo's results. So in 8 lines of code, I'm able to do a pretty sophisticated urban mapping. There's lots more science and good stuff he did to make this very easy for me to do, but this is sort of the flavor of what Earth Engine is trying to do. This kind of analysis in a couple lines of code, getting you your results in a few seconds so that you can make fast, iterative decisions and refine the whole thing down to get what you want fast. The thing you're looking at here is our code editor. That's what we're going to learn about today. It is a web-based tool. It's nice. You don't have to download anything. It does cool stuff. It's got charting. It's got maps. It's examples we'll learn about today. Just as a general wrap-up for where we're at and what's going on, this is our status. I apparently selected a presentation that's more than a year old. We actually currently have more than 100,000 researchers in 205 countries. So we keep pretty close tabs on that statistic because I'm one of the guys that does the support for all those users. So I know a whole lot of them pretty directly. When you use the system, you are using pieces that we have built. And because you're using this big, giant infrastructure that is Google underneath, you often can't do things that you think would be simple. So what you might hope is to take your Python program and say, OK, here, just run my Python program on 1 million images, please. It doesn't work that way. We can't do that because your Python program is not set up for parallelization, probably. So every single piece of the system knows how to do parallel processing because we're working on top of this giant parallel processing architecture. And what that means is if you want to add 2 numbers, it's a little tricky. There's a function called add, and you have to actually call a function, and it's a pain. If you want to add 2 trillion numbers, it works exactly the same way. So if you want to do something simple, it's hard. If you want to do something hard, well, it's actually simple. So you will find a lot of dichotomy is the wrong word, a lot of unexpectedness about Earth Engine along that way. When you sign up, you get a large quota. As long as you're doing science, we will try to support you as much as we can there. So you get 250 gigs in your bucket, which is usually enough to upload the imagery you're working with. But often you'll say, you know what, I need some more. Can I have some more? And we'll say, sure, we'll double it. And then 6 months later, you go, you know what, can I have some more? And we'll go, OK, and we'll double it again. So now you're up to a terabyte. And then a little bit later, you'll say, can I have some more? And we'll go like, what are you doing? Come on, that's a lot of storage. What's going on? But as long as you're doing science, we will try to help you. If you need 10 terabytes, I'm not exactly sure how to make that work. If you need 100 terabytes, we got to figure out who's paying for that storage. But again, for all the resources that you can actually consume by yourself, we're happy to support that for free for academic and research purposes. You're not allowed to use it for commercial purposes unless you have a commercial license. Like I said, this is an old slide. There were about 300 Earth Engine papers in 2016, about 600 Earth Engine-based papers in 2017, and we think that number is up into the thousands for 2018, but we don't know just yet. And so lots of people are making good use of Earth Engine. Some of that's just laws of big numbers, right? We've got 100,000 users, and they publish. Therefore, a lot of them are going to publish with Earth Engine. But we're pretty happy about 2,000 Earth Engine-based papers. We are working on allowing commercial users in 2018. They better hurry since we've only got 2 weeks left. But really what that means is in 2019, if you want to use this commercially, you'll be able to buy us just like you buy other cloud services, which basically means with a credit card, consumption-based billing. But as long as you are doing academic and research use, it should remain free for as long as I'm on the project, and perhaps longer. And then finally, normally I do these talks in places like Europe, and I almost never make it all the way through a talk this far without someone already asking. So when we give you our algorithms, you're going to like take them and sell them, right? Like we're giving you our IP, and that is completely not true. Our terms of service is very explicit. Your IP remains your IP. I can't even see it until you want to share it with me, which is good for you, but it's bad for me because I'm the guy that helps you when you have problems. So what happens is you'll say, what's wrong with my script? And I'll say, I have no idea, I can't see it, you'll have to share it with me. And so you'll share it with me. And then you'll say, what's wrong with my script? And I'll say, I have no idea, I can't run it because you haven't shared your images. Share your images with me. And so we'll go back and forth, and the same problem will happen with your tables. And after maybe a day of back and forth emails, I'll say, oh, look, you have a typo on line 3. And so what should have been a 15-second operation can turn into an entire day. But your stuff's really secure. So appreciate that how you want to appreciate it. OK, how does it work? What are we going to do? This is, as I mentioned, our web-based code editor. Being on the web, it's based in JavaScript, right? We wrote a web tool. Web tools are built in JavaScript. It runs in JavaScript. But the way it works is you type some code in, and you click run, and you get a result, and you can see it. The code that you type into that is also JavaScript. Let that sink in for a second. We fully understand doing large-scale scientific analysis in JavaScript is stupid, right? I get this. I fully understand the wrenching in your gut that just happened. But there's a reason for it. I know probably none of you use JavaScript. You're like, what now? The reason that we do this is that JavaScript looks and feels like every other language you've ever used. It's just like C, it's just like Java, it's a lot like Python, it's a lot like Go, Dart, C++, all those. It's sort of the neutral middle ground of all those languages, and it runs in the browser. So you don't have to download anything, you don't have to do any extra work, you just type in a little bit of code and stuff runs. And the ability to type in a little bit of code, click run, and get your results in a few milliseconds is going to change the way you do science. Or I hope changes the way you do science. Sometimes it doesn't stick. But being able to have a hypothesis, code it up in a minute, click run, and see your results in a second, and go, that didn't work, and trying something else, and trying that, and trying something else, and then trying something else, means you can try lots of hypotheses. In fact, you can try all the hypotheses. You can try them all. And you can see your results. You can run it on one area, you can go to another part of the planet, run it on another area instantly. So that ability for what we call it in the software world, rapid development, that ability to do rapid development of your science algorithm, I hope transforms the way you do science. And that's really why I'm here, is to try to convince you to do that. If you just can't bring yourself to write JavaScript, I get it, I understand, sometimes that happens. We have a Python module that you can use the same way that you use the JavaScript. And every one of you just went, that's what I'm going to do. Turns out it does not work the way you think it does, and so you're either going to be disappointed or happy, I'm not sure which. The Python and JavaScript both work exactly the same way. And in fact, we have client libraries in several other languages, and all of them work exactly the same way. Those client libraries do almost nothing. What you end up doing is you end up building a computational description in some other language. It's a functional language that we invented that doesn't have a name, but we knew nobody likes writing in functional languages, even programmers. Like nobody wants to program in a functional language. So we hid that from you by sticking a JavaScript wrapper on top of it, or a Python wrapper on top of it, or a C++ wrapper on top of it. But that code does very little at all. It just builds this description and sends that off to a server. And the server, which doesn't know JavaScript, it doesn't know Python, it doesn't know any of that stuff, executes that functional language, and that's where all the computation actually happens. So that means you can't write your Python program with scikit and numpy and pill and pandas and say, OK, here, please run this a bunch of times, because the backends have none of that. They don't have pill, they don't have pandas, they don't have scipy. So all that said, that means you probably don't really get to use all the parts of Python you were excited about using when you decided that might be the language you want. And you lose the graphical user interface and interactive development environment that we built for you in the JavaScript. So we always recommend that you start with the JavaScript, and if you really, really, really just can't stand it, move off to the Python. But the JavaScript is way easier and way faster to pick up and learn. If you happen to be a JavaScript person, anybody? Oh, woohoo, all right, look at that. That's like maybe a record right there. You are able to run Earth Engine JavaScript in Node. Anybody uses Node? No one, okay. Well, don't worry about it. Node is just a way to run JavaScript from a command line. So that if you want to kick off a job every night at midnight, you can do so without having to wake up, load the code editor, and click the run button. You could stick a cron job that will run the JavaScript for you. Anybody here an IPython notebook person? No, that's not very many. Okay, well, you can use our Python module in IPython notebooks. Specifically, we support Jupyter notebooks pretty well. But these stars, in both cases, mean you can do it, but it's a little bit like chewing broken glass. Maybe you don't really want to. And what I mean there is that there are a lot of steps to get it up. There's a lot of authentication. You need crypto libraries and all kinds of stuff to make this work. But people successfully do it all the time. So if you happen to be an IPython person, you can definitely make this work. One of my DevRel guys came to me 2 years ago and he said, I got Earth Engine to work in IPython notebooks. It's a 37-step process to set up. And I'm like, dude, that's just not going to work. Come back when you got it down to 10 or less. And he's like, I'm at 11. So he's really excited to try and make that as easy as possible. But if you try it, you're going to have problems on step 7. You're going to ask for help. We'll get you through it. But it's not a nice, easy, seamless thing to do like it is getting started with the code editor. OK, so hopefully all of you have signed up. I don't even need this slide because you're already in one of the training sessions. But we do these training sessions all over the world. I did almost 50 of them this year. I trained about 2,000 people. After this one, tomorrow we've got an intermediate one. And then later during the year, during next year, we do advanced sessions should you find this useful and want to come to other sessions. So that is what is Earth Engine. What I'm going to do next is I'm going to go through how the guts of Earth Engine work, because you kind of need to understand what you're seeing and what you're getting. If you just use Earth Engine and you make a map and you publish, your reviewer's going to go, what projection is that map in? And you'll go, I don't know, right? How to make it? I don't know, right? So that's not OK. So you need to understand some basics about how the Earth Engine works under the covers. And we will do that really quick. I say it's really quick. It's often a little longer than I expect. But oops, that's the wrong one. Here, you get all the punchlines. There we go. All right. Any questions before we start? No questions at all? That means I did a bad job. All right. There we go.
So when you're talking about the deforestation, so since you're taking an interval of like a year, 2 years, do you also account for like deforestation?
The Hansen product does account for reforestation. It's forest gain and loss. And he's not doing annual stuff. He's making annual maps. And so he's looking at every single image along the way. And so yeah, when it's deforested, he notices. When it's reforested, he notices. They're all included in the gain and loss layers.
So if like we leave an area of reforestation naturally, so we could also track that, right?
Mm-hmm.
But since the rate is very slow, I mean, is it possible to like this?
Image revisit and how often the satellite flies over, and there's all kinds of issues around that. But yeah, definitely you can track that stuff.
So is there any feature plan to include layout of the image, let's say to include the notice arrow, scale, bar?
Are there any future plans to make it easier to annotate stuff in your imagery, right? Yeah, yes. I have an entire annotation package that I'm working on when I'm not training that I'm hoping to release really soon. So it won't be everything, but it'll be a lot. It's all the stuff people have needed for the past 5 years. Finally we have, and we'll keep updating it with new stuff. But now it will be much easier to do that.
I'm just curious, why do you guys have AVHRR?
Why don't we have AVHRR? Because people haven't asked for it. Not enough people. If you want it, go click on our requested datasets page and vote up AVHRR, and then my data guys go and get it and bring it in. OK? All right, so a quick concepts talk, and then we'll stop for a coffee break. One more question.
Can we get some outputs in NetCDF and then for further analysis in another platform like
Yeah, so the question was, can you work with NetCDF files? And the answer is not right this minute. I've been pushing for that feature for 3 years. Please file a feature request saying, I really want NetCDF because my guys respond a little better to that than when I ask for it. But all that said, our data models support geotiffs and shapefiles. And if you can get your data into a geotiff or a shapefile, it will work in the system. And if you can't get your data into a geotiff or a shapefile, it wasn't going to work in Earth Engine anyway, because it's some weird shape. So getting from geotiff to NetCDF and back is pretty easy. And that's why they're not really motivated to go add NetCDF as a format. But I am pushing hard to get them to do that, because we finally found some things that geotiff doesn't quite do that we want to do. And so we're trying to make it possible to do NetCDF, or quite a subset of NetCDF, but basically the NetCDF CF conventions.
Does reprojection work well?
Does it do reprojection?
Yeah, reprojection.
Earth Engine is essentially a giant reprojection system. That is more or less the only thing it does really well, and then everything else is sort of built on top of that. But it is everything you do, for better or for worse, involves reprojection in Earth Engine. And sometimes the reprojection is nothing, but ultimately it is a giant reprojection system. And you'll see that in just a second. OK, so concepts. Earth Engine is a big data processing system. That means we have data. That means we have data models. We want you to understand those data models because it makes it easier to understand our terms, how the system works, that sort of stuff. So the first idea is the idea of a feature. This is essentially a point, a line, or a polygon, and some properties about that shape. So typically you'll have national parks as polygons, and then each national park will have properties on it like year established, surface area, water features, whatever. The map you're looking at here is a map of Nature Conservancy ecoregions. Every one of those polygons is a row in a table that's a feature. All those features have some properties, and this map is colorized by one of those properties, which I think is annual precipitation or elevation. I don't know what it is, but you get the idea, right? This is exactly the idea of a GeoJSON feature. Anybody use GeoJSON? 3, 4.5. OK, that's about right. So it is identical to a GeoJSON feature. If you don't use GeoJSON, anybody here use shapefiles? Right. OK, if you don't, maybe you're in the wrong room. It's exactly the idea of one feature or one shape in a shapefile, right? Except you can mix points, lines, and polygons in our feature collections, whereas in a shapefile they're separate things. The second idea is the idea of an image. And an image is a collection of bands. Each band has its own mask, its own resolution, and its own projection. So you can actually mix 500-meter MODIS pixels in sinusoidal projection with 30-meter Landsat pixels in UTM projection with 1-meter aerial photography photos in whatever projection. As long as they are in some CRS, some reference coordinate system, we can figure out which pixels go together, and that's under the covers basically what Earth Engine does, is figure out where those pixels go. Does the reprojection, does the resampling, gets all the pixels together, and then does math with the right pixels. Images happen to also be features. That's a little weird, but just go with the fact that they all have a list of properties, including a date and a bounding box. And the bounding box is the image's geometry, which is the same as a feature geometry. You'll see more about that in just a second. The third idea is collections of those other things. So if you have a bunch of features, they become a feature collection. And that's also called a table. If you have a bunch of images, that's called an image collection. And you can think of that as a directory of images most of the time. So if I gave you a directory full of Landsat images and I said, OK, I would like you to filter out all the images from January, you would know how to do that. Okay, so you can filter those images out and have just a small subset of images. And then I say, okay, now sort those by time. You would know how to do that, and you'd have a sorted list of images. And then I say, okay, now join those with the ecoregions table. You're going to go, what? That doesn't make sense. These are images, that's a table. It turns out that image collections are also tables of images, and you can, in fact, do things like joins on them. It's just really weird for remote sensing scientists to think about images that way. So we don't often present it. But you can actually do that. So it's sort of a wave-particle duality. Think about image collections as directories until it doesn't make sense, and then think about them as tables until that doesn't make sense. But these are semantics you can do on all collections, and some additional semantics you can do on collections are map and reduce. And those are parallel processing operations, and that's the guts of the power of Earth Engine. And so we're going to talk about map and reduce for a couple seconds here. In 2005, Google released a white paper on parallel processing methods. The one they popularized is called map and reduce. Map is just doing something to everything you've got. So if you are going to go look at every web page on the planet and pull out keywords, you're going to map a function that goes and gets a web page, pulls out keywords, and puts them into a big pile. And you can see that this computer over here talking to that web page over there has nothing to do with this computer over here talking with that web page over there. They can run independently, they can go and they can do their thing, and you can actually spread this kind of operation out over millions of computers talking to millions of websites all at once, and you just bring all the results back into what turns into the Google index. So it's a for each operation, and one of the requirements for this is that the operations are independent. This function running over here can't depend on anything from this function over here. But if you can do that, you can map. You can do mapping. And examples of doing that is if you have a table full of features and it's a bunch of geometries, and you want to know the area of each one of those features, you can see that I can send one row of that table off to this computer and one row of that table off to that computer, and each of those can compute their area independently, and then we can bring the areas back into the table, and those are independent operations. And so it doesn't matter if I'm using one computer to do that in series, or 1,000 computers to do that in parallel, or 1,000,000 computers to do it all at once. You don't know, you don't care, and we just handle that under the covers. And that's what mapping is all about. You're just saying, go do this in parallel. Let me know when you're done. Another example is if you've got a big pile of images and you want to compute cloud cover for each image. One computer can process one image, another computer can process another image, bring all the results back. This technique is super powerful, and so you might use it in lots of places you would not expect to be doing this sort of thing all through Earth Engine. You'll use it a lot in crazy ways. An example of this is maybe you want to make a mosaic for every month of the year. And so you could write a for loop and do something 12 times and make 12 images, but that runs sequentially. You do the first loop, and then you do the second loop, and then you do the third loop, and I can't really spread that out for you automatically. So instead of doing that, what you should do, or what we suggest that you should do, is you should make a list of inputs like months. So I want the numbers 1 through 12, each one representing a month. And you map a function over those inputs that says, okay, I've got a number, the number 6. That means I'm going to be making a mosaic for June. And you make your mosaic for June, and you return the result. And now I can parallelize that operation over 12 computers and do 12 mosaics at the same time. Which isn't super, a for loop of 12 versus a map of 12, big deal. But maybe you want to map a function over every day Modus has been flying. That's now close to 7,000, I think. And so that's a for loop of 7,000 is going to take a while to finish. Or maybe you want to map a function over every Landsat scene ever taken. There's like 8 million of those. That for loop is never going to finish in your browser. And so you want to use a map, and you can map over every single image in the collection very, very fast. Okay? Map. We're going to learn a lot about map today. That's half of the whole goal of the workshop, is being able to map. The other half of the goal of the workshop is being able to reduce. So once you've done something to all of these independent things, you might actually have to have some operation where you bring all the results together at once. And so when we build the Google index, that's what's happening, is we bring all those results back into one place and build the index out of those results. It's the kind of operation where the way I think of it is I have a reducer that does something, like maybe a summing reducer. This, just a tool that does sums. And then you just shove things into it and then ask it for the result. And all the reducers kind of work the same way. So as an example, if I computed the areas of all of my geometries and I went to sum all of them at once to a total area, I make a summing reducer, I stick all the areas in. When I'm done, I look inside and I see, oh, there's my final summed answer, and I pull it out. Okay, if I'm just doing one of those, that's a little silly. Maybe I could do a for loop or something that would make that easier or make it sound easier. But other places where we do this are in places where we are perhaps doing a median pixel composite. So for the entire Landsat collection, for the entire globe, you want to get a median pixel at each point. That's 500 billion pixels, or 500 billion median reductions. And the way we do that is we make 500 billion of these median reducers, stick all the pixels into them, and when we're done, we ask each one for the result. And we make an image out of what's left. So to be able to handle that sort of many in, one out kind of operation, we had to make a data concept to do it. Our data concept is reducer. And just like map, you will use it in a lot of places that you don't quite realize you're using it, or you're like, oh, I could just reduce over those. And one of them is when you train a classifier. You have a bunch of training data that has supervised labels on it. You shove all that training data down into the thing that returns a classifier, and that was actually a reduction happening in the process. There's a reducer-like system for classifiers where a bunch of training data comes in and the classifier comes out at the end. Any questions about those?
Yes.
Okay.
So what's the difference between doing a computation using a reducer? Because I'm using some fraction, etc. But you can also do it separately using the reducer command. And I get the same results on both.
You should. They're both just adding
So
or
it's
subtracting.
Just the same thing?
It's whether you did it manually or did you use the automated system to do it for you, mostly. If you want to add together three numbers, okay, A plus B plus C, great. If you want to add together 30 million numbers, it's not A plus B plus C plus D plus E. You want a reducer, and then you have some way to collect all those numbers into the reducer all at once. So for small operations, no difference. For big operations, it's really not possible except through something like the reducers.
Well, I used the image of like the global map.
Yeah, you're subtracting two images, and so it's, again, that's one simple operation. It's happening for all the pixels, but if you wanted to subtract or add all the Landsat images ever, that's now a much larger process, and you wouldn't be able to do it that way. Okay, so we're going to learn a lot about map and reduce, but I want to show you some examples. There are now many more than 8 ways to reduce, a bunch of ways to reduce, and a bunch of reducers. And this is just an eye chart to say there's a lot of them. And I want to show you a couple of them so to sort of cement this idea. If you've got a multi-band image, and at every single pixel you want to do some kind of operation like subtraction or adding or a mean, we will make a reducer for every pixel in the output, push all the values through, and get out a reduced image. So 5 bands in, 1 band out. This is the sum of all the pixels right above it. If you've got a bunch of images, and that's reduced bands. That's called reducing by band, or reducing bands. If you've got a bunch of images and you want to stack them together and make a composite out of those, everywhere that there's overlap, you have multiple numbers to do statistics with, and anywhere there's not overlap, you just have one number. And so you could be doing first or min or max or mean or mode or Pearson's correlation or whatever it is you want to do, and we'll just do that at every single pixel. And so these are 3-band images in and 1 3-band image out that is the union of all of those images, and this is reducing an image collection. You can reduce all the pixels around a pixel. This is called reduced neighborhood. This happens on a pixel by pixel, band by band basis. So these 9 pixels are all shoved into a reducer. The value comes out, and it goes back into the center pixel. And this is basically a moving window kind of reduction. You might have a region like your park or your city, and you want to know the mean NDVI inside that park or something like that, some kind of reduction inside of a region. This is called reduced regions or reduced region. And unlike all the previous examples, this one is 5 bands in, or however many bands in, and 1 number per band out the other side. So it's not an image anymore. It's just a number. What is the mean NDVI inside this image, or what's the mean reflectance inside this region? And so the numbers come out, but they're named for the band that they came from. So this is called a dictionary. Named values go into a dictionary. You'll learn a lot about dictionaries in just a minute. But 5 bands in, dictionary out. If you've got a lot of regions, they're in a table. If you want to do this kind of operation for all those regions, maybe all the parks in your country, it works exactly like reduced region, but it's called reduced regions. And those named values come out as columns, new columns in your table. So just augment your table with new columns with the results. OK? Yep.
So in the process of doing any math operation, like in this example, 5 images, is there some process like rounding, or how many digits does it conserve in the process so that we don't lose information?
All of the math operations in Earth Engine happen in double space, and you get to choose if that's what you want or not. So you can always truncate or convert to float or convert to int. OK, so, oh, yes?
So what's the case if the image has different special information?
We reproject into a common projection that you have asked for. When you do a reduced region or a reduced regions, you explicitly say, do it in this projection at this resolution. And we do everything, we reproject everything to that resolution to do that computation. I told you earlier that Earth Engine's kind of a weird system for computer scientists. Now I'm going to really show you how weird it is. When we make decisions, we always make the decision that we think the Earth observation scientist would expect. And so if you want to add 2 multiband images, what we think you mean is you want to do pixel by pixel, band by band math. Right? So the 2 pixels that overlap at the same point in the same band, you do math with those. And my computer scientist buddies look at this and go, I'm down with that. I got that, OK. But often, you will have something like an aerosol opacity image that you want to divide your entire stack by, or something like that. Right? So you might have a 1-band image and a 6-band image. And you want to do math with them. And I know what you mean. What you mean is you want me to replicate this image up into a 6-band image and do pixel by pixel, band by band math. But my computer scientist buddies go, what? Really? But I know what you meant. That's what you want to do. This is just the operations we do. And sometimes what you'll have here is a number. You want to scale your entire image by 10,000, because that's the way it was scaled. And what I think you mean is you want to take that one number, you want to make an image out of it called where every pixel has the value 10,000, and then you want a 6-band image of that, and you want to do pixel by pixel, band by band math. And this is where my computer science buddies go, I'm out. That's too weird. What we've done is called promotion. We promoted the number to a band image. We promoted the image to a multiband image. And Earth Engine does promotion for you everywhere it can figure out what you're trying to mean. If you try to add a polygon to an image, I don't know what that means. I've never seen a human do that, so I actually can't teach the system how to do that. But for all those things that we all do all the time, I want to divide 2 images, I want to scale an image, Earth Engine will do the promotion for you, and usually you don't have to think about it. It will just do it for you automatically because it knows what you were trying to do. OK? Promotion. You'll see a lot of it. All right. Getting towards the conclusion here. I talk a lot, don't I? Sorry. An example of how the whole thing works. So let's say I gave you a laptop with 8 million Landsat images on it. That's a lot, but that's the whole collection. And maybe you want to do a process to them. Maybe you want to filter down to just a 2-year region, a 2-year time period. And so from those 8 million images, you get down to 1 million images. And then for those 1 million images, maybe what you want to do is make a surface reflectance image for every one of those images. So you could take each image, process it to surface reflectance, and make 1 million new surface reflectance images. And then you might want to do NDVI for each of those. So you take each surface reflectance image, you process it to NDVI, and you make 1 million new NDVI images. And then maybe you want to make a global composite of all of those NDVI images. And so you make one 500 billion pixel composite at Landsat scale, and you squish all the NDVI images down into that composite, and you make a 500 billion pixel image. Then maybe you want to do an RGB visualization of that global image. So you make another 500 billion pixel image for your global image. And then maybe you want to reproject the whole thing to Mercator projection so you can stick it on a map. If I handed you that laptop and I said, that's what you're trying to do, you could probably figure out how to make that happen with the tools in place and do the right thing. The thing you just thought about how you would make that work is not how Earth Engine works. What happens is this process that I just described is computational description. We have think of it as a program if you like, but it's describing a way to do a computation. And this particular type of computational description is a little interesting because the output from each step is the input to the next step. And so that makes a graph, a very boring graph. It's just sort of a linear graph. But sometimes you're bringing in other data sets, like surface reflectance or atmospheric opacity or something like that. And so you actually do end up with a real graph. And that graph is what we ship off to Earth Engine. And what Earth Engine does is it says, OK, you ship it off to one computer for Earth Engine. And that first computer says, OK, I see what you're trying to do. You want me to reproject something to Mercator. So I need some inputs. So it strips off the outermost piece of that graph, takes the results, and ships that off to another computer. And that computer says, OK, I get it. You're trying to do an RGB visualization. I need some inputs. So it strips off that piece of the graph, takes what's left, and ships it off to another computer. That computer says, oh, you're trying to make a composite. I know how to do that, but I need not just one input. I need a lot of inputs. So it strips off its piece of the graph and sends what's left off not to one computer, but thousands of computers. Each one of those computers wants NDVI, so it wants some inputs. That computer that it sends off to wants surface reflectance, so it wants some inputs. Here, my metaphor breaks down a little bit. But down at the bottom, you get to the point where you're trying to pick up some bytes off of disk that are actual Landsat images. And we've now spread out over thousands of computers. That computer at the bottom of the stack says, oh, well, I only need to get this little bit of data and reproject it to Mercator. It's an important thing. We'll come back to that in a second. And give that back to whoever asked for it. And so it picks up a little bit of data, hands it up to the first computation trying to do something. That one says, thank you for my inputs. It computes surface reflectance. It hands its result up to the parent, all the way up to the compositing, all the way out to the outer edge, and you get your result. Two things have happened here. First of all, this process that we just went through is called scatter-gather. We have scattered your computation out over as many computers as we can so that each computer can do a little bit of work and return the result as fast as possible. And the reason we do this is as you're looking at a map in Earth Engine and seeing results, we're running your entire graph top to bottom. And you pan, and we run your entire graph top to bottom again. And you zoom, and we run your entire graph top to bottom again in a different projection. And you zoom again, and that's a new projection. And we run your entire graph top to bottom. So we want this to happen as fast as possible. And in general, each one of these steps is maybe 50 milliseconds. So you put together 10 of them, you get the whole thing in 500 milliseconds. You can actually get your results in half a second. This step in the middle where I'm compositing over perhaps 1 million images, that may take a little longer than half a second. But the idea is to be able to do this as fast as possible so you can see results right now. The other thing I mentioned a couple times is that we carry the projection that you're trying to use along down to the bottom of this computation. And when we pick up data off disk, we immediately reproject it into whatever computation you want whatever projection you want the computation to be happening in. And everything happens in that projection. And that'll make a little more sense in just a second. Hold on to that thought. The other thing we do to make things fast is as soon as we get in an image, we cut it up into pieces. So that Landsat scene, we cut it up into tiles. Each of those tiles is a fixed size. They're the same resolution, same bit depth, same projection, same bands, just a smaller piece of the image. OK, that's easy. But now what we also do is we take these 4 tiles and we average them together into this tile. And we take these 4 tiles and we average together into this tile. And sometimes we don't do averaging, we do sampling because averaging like classified numbers is just wrong. But what we end up doing is we end up building a downsampled pyramid. And the reason we do this is because when I'm trying to make an image like this, this is a surface reflectance composite from a year's worth of Landsat for the entire western United States. Each one of these little scales, little squares, is a Landsat scene. 20 terabytes of data went into making this image. Or that might have been the way that happened. But you're looking at an image that is only 500 pixels by 500 pixels. You're only looking at 25,000 pixels. So my options are process 20 terabytes of data at full resolution and then downsample the output, or work on downsampled inputs and just produce 25,000 pixels worth of output. And we chose the latter. And the reason we did that is because it's way faster. And most of the stuff we do in our field is linear enough that that works. Sometimes it's not, and when it's not, you can tell us. You can say, run this at full resolution. It's not OK to use downsampled pixels. That's fine. We'll do it. It will just take longer. But because I can make this kind of composite for you out of 20 terabytes of data in 500 milliseconds, that will enable you to do new kinds of science. We think that's more valuable. One more thing. As we're producing this output image, we also produce it in tiles. You'll see in Google Maps, tiles pop in one at a time because we're processing them independently. Each one of these tiles, as we want to process it, there we go. And if we're working on one single tile, to get all the inputs for that tile, we only need to get the inputs that overlap that tile. So that computer down at the bottom is picking up a little bit of data off disk, really only, probably needs to pick up a few kilobytes worth of data, reproject it right there, and return that up to the parent. So that scatter-gather at the bottom, we're talking tiny, tiny amounts of data, so we can bring it all back and do it really, really fast. Again, you can always say, don't do it that way, use full resolution, process every pixel, and we will. But when you don't care, or you don't care enough, you can get fast results that way. So that was all a very long-winded way of saying computational description plus tiling plus a zillion computers, you get your results super, super fast. OK, so we're going to take a coffee break.